So let me know if that's true. Yes. Oh, there you go. 57. Yeah, okay. So, I promised you guys that you don't have to memorize the unit circle. You can if you want to. Coordinates of the point of the circle with radius 16 corresponding to an angle of 5 pi over 9. So, real quick. On a unit circle, or on any circle, the coordinates of a point would be x, y, right? And that just relates to the cosine and the sine, right? So to answer this question, I can actually just draw the triangle. I don't have to draw a unit circle. It's got a radius of 16. Where does that go in my triangle? 16 right there, right? Isn't that the radius? No. X is x. Y is y. This is r. Yes? The hypotenuse is the radius. I like it. It's got an angle of 5 pi over 9. Now, what quadrant would 5 pi over 9 be in? How do you know that? I'm sorry?
It's like before a full pi.
Yeah, 9 pi over 9 would be that. Now, you got to be careful. What about pi over 2?
That's 1/2.
How many ninths is that? That's a little weird, but. Right. So that would be half. So half of 9 is 4.5. Is that cool?
Yeah.
So 5 pi over 9 definitely goes past that. Okay, so just figuring out where that sucker is, because it's a weird angle. It's not an angle we have to have memorized, right? 5 pi over 9 is a little more than halfway, because half of 9 is 4.5. So it's going to be a little right there. You guys settle with me? Okay. Now I want to show you a cool trick you can use. I could either set up the triangle like I have, and the fact that it's here, which trig functions are going to be, and they only want to know sine and cosine. So which of those is going to be negative? In the second quadrant, which is negative, cosine or sine?
Cosine.
Because
It's
x
gonna be
is
cosine.
Yeah, cosine's going to be negative, sine's going to be positive. I love it. So now you can just figure out the cosine and the sine of the triangle and make cosine negative, right? So this is one obviously that I couldn't put on the quiz today, because you have to freaking use a calculator for this, correct? How would I figure out the cosine? Cosine of 5 pi over 9 equals
x over 16.
x over 16. So x equals 16 cosine of 5 pi over 9. You just throw that in the old calculator, right? Now the answer is going to be
Negative.
Yeah, I gotta be a little careful. All right, let me see.
Why
This
wouldn't it be x
should be-
equals 16 divided by cosine? 5 pi.
All right, so
Because you flipped them.
if I go to solve this,
Mm-hmm.
I'm just gonna multiply by 16, correct? You with me?
Oh,
Yeah.
okay.
Okay.
Yeah.
Now here's the cool thing. Is this a reference angle? Did we use a reference angle?
No.
If you have your calculator, make sure you're in what?
Radians.
Radians. Do 16 times cosine of 5 pi over 9.
Negative 2.7.
It's already negative.
Mine says done.
What is that? Wait, I didn't get it.
It's a very honest calculator. I love it.
What is that?
Oh, wait, hold on. I don't know. Mine says done.
Let me see it.
It says done.
I've never seen that before.
All right, that is kind of hilarious. See if it's just the way it was put in there. Oh, I think it is done. Your calculator's done.
Oh,
The
did it?
calculator is, it's
just
screaming,
died.
it's screaming for help.
It just died, didn't it?
It sort of did.
Okay.
Let's see if I'll give it one more try here. Oh, there it goes. Okay. All right. So there's a couple things going on here that I need to kind of be careful about. Okay.
15.993.
Go with me for a second. And you guys are like, that's all I ever do. If I wanted to draw the triangle, I'd have to use this angle here. Is that cool? What angle is this? What's in here? This is 5 pi over 9, and that's 9 pi over 9. How short am I from this? This is 5 pi over 9.
3 pi over 9.
4 pi over 9.
Wait.
Yeah, I've got to go 4 pi over 9 more to get from 5 to 9. Okay, so this will be 4 pi over 9. So if I drew the triangle, it would actually need the reference angle in there. And then I would have to make the answer negative. The really nifty thing, the thing I kind of mixed up in my brain, I want to show you this second. If I just use the angle given, not the reference angle, if I'm just throwing it in the calculator will of course give me the correct negative or positive. Because it knows 5 pi over 9 is in the second quadrant. That's why your answer came out negative, correct?
Mm-hmm.
So then I don't have to put a negative on there. It just happens, right? So here's a beautiful thing. Let me go ahead and do this. I wasn't sure when I was going to do this, but obviously I can just do it right now. Because it kind of sucks when the book's approach doesn't jive with mine. Here, you just take these. If I have a radius just sitting somewhere, this is kind of cool. It doesn't matter, Jeff. And I want to know what the x and y piece are for that. Right? I want to figure out the x piece and the y piece. And I'm allowed to use my calculator. I don't need a reference angle. I could just use the angle given. Why do we need a reference angle? Because what do we have memorized? First quadrant stuff. Reference angle always takes me back to the first quadrant. I can then I don't have to memorize as much. So watch this. For example, if my radius was 5, and I'm at an angle of, what you got, Jeff? Let's go with, you could do it, buddy, 8 pi over 7. Do y'all agree with me that would be in the third quadrant? Why would that be in the third quadrant?
Because 7 pi over 7 is pi.
It's a full pi.
And it's
a little bit more,
pi
correct?
over 7
Now watch.
more.
If my only concern is to just find sine and cosine, it's not an angle that I know, I don't need to do reference angle. Watch this. What should both sine and cosine be? What should be true about them down here? They both should be negative. So watch. Couple things are going to happen here. Sine likes y. Cosine likes
X.
Let me see if you guys will be cool with this. I'm going to lay something on you. It's a little bit before I was going to, but I think this is a good time to do it. One way to look at sine is interesting. It's not, what I'm about to say is not true, but it's a way to remember stuff, right? One way to look at sine, this is the way I look at sine. It's the percentage of the hypotenuse that lies in the y direction. Isn't sine always, what's the biggest sine can be? 1, so that'll be 100%. So at 90 degrees, what percent of the thing is lying in the y direction? 100% of it. Sort of with me? So watch this. What percent of this is lying in the y direction would be 5 times sine of 8 pi over 7. So this percent of 5 is lying in the y direction. And it's going to come out negative because it's pointed down. So try that in your calculator. And if you don't have one, you can come grab one. I've got some. See what you get.
Negative 2.16.
Do it again, sorry.
Negative 2.16.
16? Okay. And now, how do I get the x piece? What do you think I do to get the x piece? What likes x? Cosine. So if I do 5 times the percent that lies, the percent of 5 that lies in the x direction, it's going to be bigger because it looks like it's
-4.504.
stuff. Okay. Gotcha. Okay. So that is another way to sort of look at what these trig functions do. If it's a value that we know, I need to do reference angle because I don't have 210 degrees memorized. I have 30 degrees memorized, correct? If I'm allowed to use the calculator to do it because I gave you a weird ass angle, the calculator can just take that angle. It doesn't need a reference angle. And the really cool thing is the sign SIGN, the positive negative, comes out automatically. Because it knows 8 pi over 7 is down there. Okay, maybe. Okay. So if it's a problem that you have to do by hand, I would give you obviously an angle that you're supposed to have memorized, and you would find the reference angle because that's how you have things memorized, right? Back in the first quadrant. If I'm allowed to use the calculator, it could just eat up the freaking angle I'm given. Because that tells it which quadrant things are in, and it gives me the right SIGN. Sucks I'm in a place, for every math teacher we get to trig, and we're like, well, we got to spell out the word sine to know which one I'm talking about. Okay. Is that all right? Okay. Anything else? One more question from homework, maybe?
Well, something from the quiz, actually.
Sure, yeah.
The last thing there where you like brought the exponents down in the
Yeah.
the natural log. I didn't know how to go after I
So-
got it down in the natural log.
Everybody had this problem, but nobody had this problem, right? Okay. First step.
I
Take the
took
natural
X
log
plus
both
4
sides.
and the X down.
Not yet. Can't do that yet. Okay. If I take a natural log both sides, then I'm allowed to bring these down because it's a property of natural logs or any log, right? And then we just did a problem like
And
this.
then you distribute
Yeah.
the natural log
Distribute.
of 7.
And then the XLN7 you're going to bring over there, right? Yeah. And again, it didn't matter that you didn't have a calculator because that would have just made it have one more step. Not having a calculator, you just didn't do that extra step, right? Yeah. Yeah. Then you subtract this over and you divide. Yeah. Right?
So you can't do natural log 7x plus natural log 28?
Oh, no. Okay. Is 2 square root of 7 equals square root of 14? So in general, there are very few functions where coefficient in front of a function can just come into it. Right? The most common mistake I see is something like twice x plus 2 squared equals 2x plus 4 squared. You guys see that that's a mistake? Do you guys see that that's a mistake? Now, I could have just went and said, maybe that's fine, right? But that's no good. I know it. What mistake did I make?
You didn't treat X plus 2 as a quantity.
I have to square for it. Yes, it's just a PEMDAS. So real quick, how many? Do you see how many factors of 2 I have now? I have 2 of them, don't I? But I only had 1. How the hell did I do that? Does that make any sense? So that's no good. And it's believe it or not, it's exactly the same mistake as making this 28 because you've taken, here I cannot take a number and multiply it into a square problem. Here I cannot take a number and multiply it into a natural log problem. I can't do that. Okay, I like it. Very few functions have GCF ability. That something just comes right out. Very few functions do that. Okay. All right, so I've got a couple things to finish up from chapter 7, and then we're going to get a little bit into chapter 8. As a math teacher, I am used to a reaction like, one thing I want to point out, and this is going to become very important very quickly. And this is a little bit weird of a way to look at this, but can somebody remind me what even and odd symmetry was? What was even symmetry?
That's a great question.
Well, like an even
It's a great
function versus an odd function?
I should have put that on the quiz. Let me see. So even symmetry. Remember end behavior?
Yeah.
Okay, what was even, what did an even power lead to? Yeah. Okay, so even symmetry basically is 1. So a parabola is the most basic example of an evenly symmetric function. And one reason we call it even symmetry is because this would be x squared, even power.
Okay.
So even symmetry essentially says it's reflecting around the y-axis. So, no. Section 7.4. And then it's going to lead into chapter 8, yeah. So if there's a point here, 2, 4, then there's also a point here, negative 2, 4, right? So here's a test for even symmetry. If I have a function like x squared, when I plug a negative x in, so if I put a negative input in and the output remains the same, that's evenly symmetric. So what happens when I put a negative x in?
It's gonna be x squared.
Yeah, so it's the same thing. Stayed the same. So it's got even symmetry. Kind of gave up on the word symmetry there, but. All right, so what about odd symmetry? What was odd power? What kind of end behavior did that lead to? Cactus, I like it. So here's, as I'm doing this, I'm remembering that we didn't really do much with this yet, so okay, that's fine. So this would be the end behavior, so let me fill this in. So a cubic is a most basic odd symmetry, and again, you see why we call it odd symmetry, because it's based on a function that has an odd power, right? So a function could have odd or even symmetry and not be polynomial. It's just sort of where they get their name from. What kind of symmetry is this? Is it reflecting across the x-axis? Is it? Did it just reflect across the x-axis? No. So here's the weird-ass symmetry. So my scale is freaky, and I don't care. So when I put a 2 in, I get 8, correct? 2 cubed is 8. What's negative 2 cubed? Negative 8. So this is, you ready for this? This is called symmetry through the origin. So if I draw a line from a point through the origin, it ends up at a point on the other side. So odd symmetry is appropriately named. It is very odd. The mirror is a single point. It's the origin. How do I test for odd symmetry? Well, if I plug a negative in and the answer comes out the negative of what it used to be. So what do you get when you plug a negative in? Yeah, negative x cubed is negative x cubed. So isn't it the opposite of what it was to begin with? So that would be odd symmetry. So look at what we know so far. We haven't, so chapter 8 is all about graphing these trig functions. We have not done that yet. When we're looking at something like this, yeehaw, and I look at, like, for example, 45 degrees. What is the sine of 45 degrees? Rad 2 over 2.
2 over 2, yeah.
To check it for symmetry, let me put in the negative angle. Where would negative 45 degrees be? Where's negative 45 degrees?
It'll be right under it.
There, right? All right. What sine of, you can do it, Jeff, sine of negative 45 degrees?
Negative.
Negative rad 2 over 2. So what kind of symmetry does sine have? Odd symmetry. When I put a negative input in, the output becomes negative. What about cosine? What's the cosine of 45 degrees? Holy shit. And what's the cosine of negative 45 degrees?
Rad
Careful.
2 over 2.
Don't they both have the same? Now my poor circle is really shit. I'm sorry. I draw the poor. But don't they both have the same x piece? So they're both Yeah, so when I put a negative input into cosine, the output stays the same. So sine has odd symmetry. Cosine has
Even symmetry.
even. Did I just say that right? Jeff, you could do it, buddy. So when you put a negative in, the output's negative. Yeah, you're good, Jeff. Even symmetry. Okay. It's a little trippy to look at the unit circle. Do you guys all understand that this is not somehow a graph of the sine or cosine function? This is just a unit circle, and cosine and sine are a piece of it. So what we're going to do is we're going to finally graph these trig functions. One little thing I want to show you on your calculators real quick. If you have your calculator, could you tell me, make sure you're in the right mode. Let's do degrees. Sure. Could you tell me what the cosine of 111 degrees is? Yes, the cosine of 111. Make sure you're in degrees, right? So you get negative 0.358, blah, blah, blah. Okay. What would the secant of 111 degrees be? What is secant defined to be?
It's the reciprocal.
1 over
of
cosine. So I could just do 1 divided by cosine of 111. That would be secant. Because I don't know if anybody out there was like, okay, I see sine, I see cosine, I see tangent. Where the shit is secant, cosecant, and cotangent, right? Well, now you know. I just do 1 divided by. So if I want tangent of 3 degrees, I would, a cotangent of 3 degrees, I would do 1 divided by tangent. Don't do that, Jeff, of 3 degrees. Bam! Okay, how we doing? Just wanted to point that out. That you can get all 6 trig values on the calculator. You just have to do 1 divided by for the reciprocal functions. Okay. All right. Remember. Now, let's do this. Now we're going to step fully into chapter 8. So now we're going to look at this sucker as a function by itself. So when I draw the unit circle, it's not a graph of any function. I can identify all 6 trig function values at any angle. It's not the graph of a function. Bless you. So whenever I'm faced with a function that I have no idea what it looks like, and I know some of you guys know what this looks like, but let's pretend like we all have no idea. What do I create to help me graph this? No. Any function, if you don't know what it looks like, what are you going to start to do? How do you plot? How do you graph a function? You plot points. So I'm just going to make an XY table. So let's put some smart inputs in here, like 0, right? What's the sign of 0? 0. Sign likes Y. 0 is all X. Okay, I like it. Stick it with radians, by the way. What's another good one to put in? Don't go to pi over 2 yet.
Pi over 6.
Sure. All right. Pi over 6. What's that?
It's gonna be
Careful.
1
That's
half.
30 degrees, right?
Maybe
So
1/2.
I haven't gotten very far away from the x-axis yet. So sine is still a little. Yeah. I don't know if that helps you guys. I mean, I kind of like the idea of a turtle. So if I'm on the x-axis, the sine turtle's like, holy shit, I don't like it here. If I get a little bit away, he's like, oh, okay. And then the further I get away, oh. And if I'm at the y, he's like, totally, yeah, dude. My little turtle's doing it.
That's what I was gonna say. Pi over
Pi over
4.
4.
Nifty. And what's that?
No.
Now we're going to graph this by hand. Let's be nice to ourselves. 0 is 0, Jeff. That's amazing. 1/2 is 0.5. That's amazing. Root 2 over 2. That comes out to be roughly 0.7. You can check me. Pi over 3. What is that in degrees? Pi over 3. 60 degrees. Okay, cool. With sine is 60, and you can kind of see the pattern developing here, right? Rad 0 over 2, rad 1 over 2, rad 2 over 2. Rad 3 over 2. Kick ass. Rad 3 over 2, I don't have memorized. I think it's about 0.9 almost. Can you check me on that?
0.866.
Okay, so we'll round to one place because we're going to graph these by hand. So as horrible as my graphs are, I couldn't do better than one decimal place. Okay. And then the next one obviously is pi over 2, right? And that's where it's 1. I like it. So what's going to happen after that? What's the next good thing to plug in? Well, if we went, we don't want to go, right? When you go, that would be way down here, right? So let's do this. You guys can obviously have,
2 pi over 6.
for right now, you can have this sitting next to you, yes? So 2 pi over 3 is a good one, right? I want you to realize something. Notice what's gonna happen. So the y piece is equal to the output for sine. Does that make sense? Because sine likes y. Here it's grown to 1/2. Here it's grown to root 2 over 2. Here it's grown to root 3 over 2. Here it's grown to 1. Now it's going to start to shrink in exactly the same way it grew. What does that mean in my table? Well, that's going to become 0.9. Right? What's 3 pi over 4 going to become? Now I'm just going backwards, right? 0.7. And then 5 pi over 6. 0.5. And then pi, 0. Does that make sense? As I am on the x-axis, if I start to rotate, I'm getting bigger and bigger y pieces, right? And then, of course, if I keep going, I'm like, oh, man, shit, now I'm losing y's as I go backwards. My triangles are getting smaller and smaller y pieces until I get no y piece. Then what's going to happen past that? It's going to do all that again, except now it's going to be negative. Okay, cool. So what the shit is this thing going to look like? All right, let's take a look.
Sine wave.
That is so true. Okay. So I'll give a little bit of detail. What kind of scale do you think I want to use here? What's the biggest sine can be? 1. And what's the smallest sine can be? Negative. Yeah. That's a beautiful scale, Jeff. That's almost good. Okay. So 0, 0, right? 0, 0. Pi over 6 is in here. Let's not worry about it. Let's look at the pi over 4s. Pi over 4 is 0.7. This is 0.5, so pi over 4 is 0.7 is about right there. Pi over 2 is 1. Okay, so pi over 6, I didn't really put the scale that good, but pi over 6 would be 0.5, it should be right there. So you can see it growing slowly. Then it starts to shrink back down exactly the same way. So now it's at 3 pi over 4, so it's going to be 0.7 again. And then it's a pi, it's going to be 0 again. So it's got this kind of like, wee. Huh. So as it approaches 90 degrees, it slowly grows. As it approaches 90 degrees, the y side slowly grows. Once it's past 90, it starts to shrink again because now I'm getting less and less y, more and more x. What's it going to do over here? One thing that's going for sine for damn sure is it's repetitive as hell, yes? All of these things repeat, and that's why they are called periodic functions. Any function that repeats has a certain period. It repeats over a certain amount of time. What's it going to be past 180, though? It's going to have all the same values, except they're going to be negative. So now it's going to go at, let's say, for example, 3 pi over 2. It's going to be -1, right? 3 pi over 2, -1. So at like this one, it's going to be at the pi over 4, it's going to be about 0.7. So it's going to repeat that same dome shape just on the negative side. Go ahead.
Why did you use those values? Like, did you specifically use those values?
Say again.
Why did you use those values for the
Oh, just to make an easier scale. I didn't want to make a scale of pi over 6 necessarily, but I do want you to know, you can see pi over 6 would be in here, so 0.5, sure enough it goes through 0.5. Okay. So, if you think of this as the Earth, the northern hemisphere sign is positive. That's what this is. It's positive before it gets to 180, then it's negative, and it repeats all the same values. They just have negative signs. What's it going to do after 2 pi? When it gets back to here, it's going to do the whole thing again, right? So it's going to keep going, and it's going to keep going back here. So, of course, if you ever watch any horror movie or whatever, very often in the background they have these oscilloscopes, and you'll see it having the sine wave going off, right? Or if you do any sound work, you've got to be careful about your gain. You don't want to flatten the top of your sine waves and so forth, yes? If you got it too cranked up too much, then it goes, you know, and it does not sound good. Yeah, you could get a square wave. You could get a sawtooth wave. But anyway, that's fine. We could do something very similar for cosine. How do you think cosine's going to look compared to this?
The other way.
It's going to have the exact same shape. You with me? Because don't cosine and sine, they basically spit out the same values, just offset. How much are they offset by? How much are sine and cosine offset by? What is sine of 0? 0. What's cosine of 90 degrees? 0. You with me? So they're offset by 90 degrees. So if I want to graph cosine, here will be a little less detail oriented this time. Pi, 2 pi, pi over 2, 3 pi over 2, 1, negative 1. What's cosine of 0 again? Cosine of 0? Cosine of 0 is 1. So sine gets to its highest point 90 degrees after cosine does, right? So cosine's already max, so it's going to go down from there. At 90, it's 0, correct?
Yeah.
What about at pi? What's cosine at pi? Where's pi? Is it,
0.
which axis
No,
is pi?
1.
It's 0.
1.
Negative 1, because it's pointing back, right? So now it's negative 1 here, and then it's going to go back to 0, and then it's going to go back to 1, because then it starts to repeat again. So now it's going to keep going forever this way and forever that way. So it's just, do you see if I just shift this over, they look exactly the same? Whoops, if you could see them both, that'd be great. Oh, I'm as out as I can be, really? Poor little dude. There. It's got the same valley here, it's just shifted over by 90 degrees. Okay. You guys with me? Let me ask you a question from either one of these. What would you say, what do you think of when I say the word amplitude?
Oh, that's.
Anybody have any idea about amplitude?
Yeah.
Yeah. So the amplitude
That's why.
is basically how far it gets away from its middle. So would you everybody agree that the x-axis is basically the middle?
Yeah.
Yeah.
How far does it get away from the middle?
1.
1. So the amplitude is 1.
Yeah.
How do you think I would change the amplitude? What if I wanted a function so when I graph it, the amplitude is 2?
By multiplying it.
Yeah, I'd stretch it, right? Which means multiply the cosine by 2, and now suddenly it would just be the exact same shape, just stretched so it goes to 2 and negative 2 instead of 1 and negative 1. Are you guys with me? What if I wanted to change the midline? What if I wanted just to move the whole thing? Yeah, then I would add or subtract. Oh, what does this sound like? I mean, this is just the transformations, right? What if I wanted to move it left to right?
It would have to be with that.
I put it inside. I love it. Okay, maybe. You guys? So all that same stuff comes back. Cosine and sine, they're just functions. What can I do with every function in the entire universe? I can move that shit around, right? And we know exactly how to do it. I don't care what the function is. If I replace x with x plus 1, it's going to go back 1. I don't care what the function is, right? Okay, maybe. What about, let me do this since we have this here. I've got sort of a, yeah, okay. Real quick, what do you guys think about, remind me what cosecant is all about?
It's the opposite of
Be careful. Reciprocal. Don't say inverse, be real careful. Real quick, what's the input of a trig function? What's the input of sine, for example? What does it have to be? The input of sine has to represent a what? Angle. You guys with me? The inverse function's output would be an angle. So we are not talking about inverse functions at all yet. So we've got to be really careful with their language. I know that if I say, what's the inverse of 5, you might say 1/5, right? But we have to be really, inverse function means something very specific. It's the function that undoes something else, right? Let me kind of throw this at you just because it came up right now. What's the sine of pi over 6? 1/2, right? Is that cool? So what's the inverse sine of 1/2?
5 or 6.
5 or 6. So the output to an inverse trig function is an angle. Which angle? The angle that makes it equal to this, right? So we're not there yet. I just want to throw that. That's a question I can ask you right now because it's. Now here's another little thing, real quick, just because I happen to be talking about this. Is this a 1-to-1 function? What was the test for it?
The horizontal.
The HOLT, yeah, the horizontal line test. Do you remember what we did for stuff like parabolas so that we could force them to be invertible? Didn't we have to?
We had to cut off.
We had to restrict the domain, right? So, okay. I'm sorry. That's a little preview. Later we're going to do that. Okay. But thank God, inverse functions, they always do the same damn thing. Whatever the original function's input was, the inverse function is going to be the opposite. It's going to be the output, right? Okay. So cosecant. It's 1 over sine, yes? Okay, so watch this. What time we got? Oh, good. Let's just do this one more thing. All right. It's probably not going to show up anyway, Jeff, but we got to try. So like right here, wouldn't 1 over sine be 1 here? Because it's 1 there. Isn't sine 1 here? So wouldn't cosecant be 1 there? Because 1 divided by 1 is 1, right? At pi over 6, what's sine? 1/2. So what would cosecant be there? 2. So this will be at pi over 6 to be up here at 2. Well, pretend like that's 2. What's going to happen here? Where the output of sine is 0, what's the cosecant? What's happening to cosecant? It will be 1 over 0. So we already talked about this. It'll be an asymptote here. And look here. At this pi over 6, it's 1/2, so it's going to be 2 again here. So this is kind of nifty. I want this to... If the number is less than 1, won't 1 divided by that be bigger than 1? So for example, is 1/8 less than 1? Yes, 1 divided by 1/8 is 8. So it gets way bigger than 1, correct? So as I get closer to 0, my outputs are getting smaller and smaller. So for the cosecant, 1 over that is going to get bigger and bigger. It's going to approach this asymptote. Why is there an asymptote here again?
Because
Sine's output here is...
sine's output is 0.
Which means cosecant's going to have a 0 on the bottom. That's an asymptote, right? So what, you notice something kind of cool? If I graph sine, I just have to put these cups there. Now I've just graphed cosecant. Because cosecant is 1 over sine. So when sine is 1, cosecant is 1. When sine is 1/2, cosecant is 2. When sine is 1/100th, cosecant is 100, right? Okay, maybe we'll do more with that. Just to kind of put something in your head, if I wanted to do tangent, I could kind of think of that as sine over cosine, right? I mean, this is the one we definitely talked about. Does cosine ever 0? Is cosine ever 0? So will tangent have some asymptotes? Okay, good. Okay. All right. I think that's enough. That's enough for today. By the way, our next test is not next week, right? You guys see where it is? It's the Monday after next week, yeah.
Oh, the new.
Okay. Things change. Okay. So let me know if you have any questions. Otherwise, have a good weekend.